Hi, everyone. Thank you for coming to this talk. It's my greatest pleasure to welcome Dr. Yuandong Tian, a very special guest to give a talk in our department today. Yuandong and I have known each other during my work at Facebook Research a few years ago, and he's been a very inspiring researcher to me personally, and I remember having many insightful conversations with him. And currently, he's a research scientist and also a manager at Facebook AI Research. Previously, he also worked at Google self-driving car team, graduated with a PhD from Carnegie Mellon University in 2013, and a bachelor from Shanghai Jiao Tong University, which happens to be my alma mater as well. And his work really touches on many important aspects of AI, which includes deep reinforcement learning, multi-agent learning, and theoretical analysis of deep models. And some of you probably heard of this OpenGo projects where he is the lead scientist and engineer on. And today he will be sharing with us his recent work on understanding deep models with teacher-student setting, and really excited to learn more on this front. And with that, let's welcome Yuandong and give our full attention to what he brings us. Yuandong, feel free to take it away. Thank you.
Thanks, Sharon, for introducing. My name is Yuandong Tian. I'm a research scientist and a Y manager in Facebook AI research. So today I'm going to talk about understanding deep models with teacher-student setting. So I think I first want to introduce myself a little bit on like what I've been working on during this years. So I'm first a PhD in Carnegie Mellon, and then I spent like a year in Google for self-driving car, and then after that I moved to Facebook AI research until now. So I think in my research, there's actually two trends. I always like two threads that's going on. One is more on the empirical side, the other is more on the theoretical side. So on the theoretical side, I basically understand models and algorithms. In the empirical side, I first work in computer vision. Now I'm switched to a little bit to reinforcement learning and also deep reinforcement learning. So let me introduce a little bit about the highlight of the work that I've been involving and also leading. So I think during PhD, I think I've been mostly working on how to basically estimate the deformation, right, in image given the two images. So I think I'm honored enough to have share the same advisor as Mohit Gupta, who is a professor here. So basically, like in this work, we are trying to find a like principal way to understand how can we actually get like the parameter of the deformation in control sample complexity. And one of the people actually got like all Marpress also mentioned. So I think after this, I moved to Facebook. Then I'm basically working on like computer Go, and that project actually like before AlphaGo, and we actually get like pretty good performance after that. And one of the interesting highlight is actually I was basically playing with the AI to compete with one of the professional players, Koichi Kobayashi in Japan. And that's a very interesting experience for me. And I think after that, after AlphaZero comes, so we have this OpenGo project. And that project basically reproduced AlphaZero and use that route to basically show that this approach is reproducible and understand a lot of details about how and why this thing can work. Right. So basically, we have open source the code, and we show that our bot is strong enough and have beat like professional players by 5-0. Or straight for 4 professional players in Korean Go Association. So, and recently I've been working on like contract bridge. And so one is basically like the game is actually much harder than complete formation game which is like Go or chess. In this case, like people only see their own card in the bidding phase, and we want to understand what is the signal that other teammates is sending you and also are sending you. So I think one of the interesting thoughts here is that we actually can find a new theoretical framework for multi-agent collaborative game, so that if you use that for training to improve the collaboration between partners, we actually can achieve state of performance on bridge bidding. So that paper was accepted in Europe. So I think, but for today, I'm going to talk a little bit more on the theoretical side of the work. And so we all know that deep learning has been made a tremendous success in terms of lots of different areas, like computer Go, like chess and StarCraft, and also maybe in the vision side, we see like super strong vision models since the appearance of the AlexNet, right? So we now see like a superhuman ImageNet performance, right? So in classification and also with detection system that is much better than the pre-deep learning era situation. And we also see the same network being, or the neural network being used in different scenarios, like speech recognition, right, image, and also natural language processing. And recently, we also see GPT-3 that is able to generate like a very interesting sentences that look like how basically this is like how human this look like these sentences are written by humans. So, and we all see all this like great success. But like one interesting question actually remains, right? So how do deep models work? Right. So that's actually like a very hard problem to understand by itself. And right now, so for most of the empirical study, what we do is we treat it as a black box. And we say, okay, the black box take the input, and then we train the black box so that it will align with a given output. Right. So, and then we basically say, okay, we train a black box, and hopefully the black box will do very well in a new data set, and we solve them for the problem. Right. So this is actually like a good perspective in terms of like abstraction and understanding how deep learning works. But from a theoretical point of view and from a more scientific point of view, we would really want to open the black box so that we understand things much better. So in order to understand how deep model works, there are three different aspects we want to think about, right? So one is the expressibility. So what I mean by expressibility is you want to know how powerful is neural network, right? So if you use the linear model, then the linear model is actually not that powerful. We know it cannot solve the problem of XOR. Right? So the XOR problem is exactly shown in the slides. You have 2 plus and 2 minus. Positive sample and negative sample, and they are basically ordered in this kind of diagonal manner. So in that manner, if you use the linear classifier, you have no chance to separating positives from negatives perfectly. Right. So in order to avoid this, one thing we could do is we can train a neural network, and so that the decision boundary is actually curvy, right? And then you basically separate positives and negatives with perfect accuracy, right? So people in 1980s, they already proved that neural networks is a universal approximator, which means that for any arbitrary function, you could imagine, I mean, if you have a 2-layer neural network with exponential number of hidden neurons, then there exists a set of parameters so that this neural network can fit to any function. Right? So this is something that already proved, and people know that for a long time. Right? But if we just have expressibility, this is not enough at all. The reason is that there's a lot of other models that has the same expressibility. Right? So people might, one simple thing we could imagine is the nearest neighbor. Right? So k-nearest neighbor or nearest neighbor is also a very powerful machine learning models. The reason is that if you fill in the entire space with exponential number of samples, then you are guaranteed to get a bounded error for new data with the label. Right? So this is a very trivial but an interesting statement, saying that you can always get very strong, good models to show use that model. You can actually have bounded errors, but that actually requires exponential sample complexity, which is not achievable. Right? So that's the reason why we are so interested in deep models, in which they seem to be practically working super well with a lot of data, but not exponential data, but still can generalize to new data set. That's something that is very interesting, which is the generalization component. So in generalization component, what we're actually thinking about is not only the expressibility, but also we want to say, okay, does zero training error actually leads to overfitting, or does more parameter may lead to overfitting, something like that, right? So you basically want to see in a new data set, what is the performance that you can achieve if you already do very well in the training, right? So between generalization and also expressibility, there's an intermediate question called optimization. So in that question is, okay, we know the model can achieve real good performance, right? And the model has strong expressibility, but can we reach to that place? right? So you're starting from a very interesting starting point. And then with some algorithm, the algorithm will like iteratively change the parameter until it end up with some local minima. And you want to show that that local minima is good, or it does not really suffer from gradient vanishing or exploding problem, etc. So you have this kind of three different aspects of how we should understand deep model works. Okay, so one of the very traditional approach of solving this problem is a problem setting is about supervised learning. So what I mean by supervised learning is you have a data set, and data set is basically a set of like a pre-collected data with input xi and also yi is the label, right? So you basically use the input and output to train a network so that the network will behave like what you want it to be. Yeah. So the good thing about that is that it's a very simple setting, and everyone knows that, everyone understands this is the case. You collect data, you label them with Mechanical Turk, and then you train the model on a new data on a network. That's it, right? But here in this talk, I'm going to talk about a little bit different setting, which is the student-teacher setting. So the setting is kind of different. So instead of having a data set, as a teacher, we want to remove the data set, but replace that by a teacher or Oracle network, which has fixed parameters. Okay, so the reason why we can do that is because the network has a strong expressibility. So you can say for any data set there exists a teacher, so that the teacher can replicate the labels. Right. So if that teacher exists, then we just place a teacher there, and then we want to see in this new setting what can we say about the training process. Right. So the good thing about teacher-student setting is also threefold. Each of these bullets corresponds to the previous three bullets. So first of all, for expressibility, we now know that we have a function here, and the function is the teacher, right? And we know that if the student is sufficiently complicated, more complicated than the teacher, then definitely we can find a best solution ever, right? So this will basically solve the expressibility issues. And also the good thing is the teacher now serve as a role model for the student to learn from, right? So in terms of like studying optimization, then we can actually study not only how the loss drops over time, but also how the internal dynamics of the student changes according to the teacher's internal weights. So then we actually can study like a very fine dynamics behavior by comparing with a teacher. So that's a very good thing, because now we have more to see and more to check rather than just staring at the curves of the loss functions. Right. And finally, I think this is something that I'm focusing on in the next few slides, is about like how can we actually achieve generalization. Right. So we see the teacher setting. One good thing about that is because teacher actually governs the input-output mapping. So if the student not only learn the output of the teacher, but the student's weights actually get specialized or get aligned with the teacher, then we could expect that the generalization is better. Because if the student actually learn the extent of the teacher, then the student expect to give you the same label, consistent label of the teacher with the teacher if they have the same data set as the input. So that's actually like a very interesting way of solving this problem compared to this generalization in the data sets. Okay, so there's like a very old history of teacher-student setting. So this is not a new thing at all. I mean, if you check the history, what happens is you see like in 1995, we already see a very simple student-teacher setting coming out. And basically, like, they are not coming out for the machine learning papers. They are basically publishing papers on the physics reviews. So in that case, I think physics people actually try to understand things, try to use their mathematical tools to understand what deep learning works. So that's but in that setting, we basically don't see ReLU here, because ReLU was discovered after the deep learning era. So people don't use ReLU. People basically use Gaussian input. And they assume that everything is, and also they assume that the input dimension is super high. And then like you can use that to prove a lot of things in the thermodynamics limit. Right. So in these cases, they basically only analyze like one layer of trainable parameters. Right. They use nonlinear functions. This is the Gaussian error functions, right, as the activations. And because why they are doing that is because with these nonlinear functions, you can actually integrate everything out if the input is Gaussian. Then you have analytical solutions, and you use analytical solutions, you can talk about a lot of details about what's going on inside the teacher-student setting. So one interesting conclusion of this sequence of work is that they basically show that you can see specialization between teacher and student. So that's actually a very interesting solution, but they are not able to push things a little bit further because of this very strong assumptions. Okay. So so then like the time goes, and then in 2017 or 2018, then people start to actually see these values of this teacher-student setting, and lots of papers actually trying to use that kind of framework to do analysis. So I'm also involved a little bit on this kind of trend. Right? So this here's like one of these example papers that I'm basically in that paper I'm trying to use the student setting to analyze what's going on with the dynamics of the weight. But in that case, like because the input is Gaussian and there's a bunch of assumptions, so we are not able to show there's a specialization, but we actually see an interesting behavior of the gradient when you doing gradient descent. So basically, that gradient can be composed into two components. One is the linear component that is assuming that there's no teacher. There's no ReLU, right? There's a nonlinear components because of there's a ReLU gating. And if you put these two together, then you see very interesting dynamics between the two. And in some cases, you can even prove that it's convergent to the correct parameter of the weights. So now people may wonder, okay, what happened to multi-layer? Right? So in a multi-layer setting, we haven't seen like a lot of works on that in the teacher-student setting because it seems to be super complicated. But interestingly, if the teacher and student they're aligning with the L2 norm, and they are of the same depths, then and also the activation function ReLU, then we have very interesting results for one of the for all these cases. So here's like one of the interesting cases that we want to discuss in this talk. So in this talk, what we want to say here is that we want to show that the students' neurons is aligning with the teacher's neurons at every layer, even if there's no direct supervision between these layers. Right. So in order to achieve that, we have to first define what is the specialization. I have already mentioned that word a couple of times. And so here, the specialization is basically defined as if you check the boundary of the two nodes, one is from a teacher and the other from a student, their boundary want to be aligned with each other. Right? So if you draw the boundary in input space, and this boundary should be very close to each other. Right? And then the angle between the two is basically like the epsilon or the theta that is basically measuring the degree of alignment. Okay. So once we have the definition, then the question is, can we quantitatively show if the training has already done with small gradient and whether the student will align with the teacher? That's basically one question that is answered by the paper. So if that's true, then we can naturally make the conclusion that if you have a small training error, and that will lead to a very good generalization. So this basically shows that the student actually learn the teacher not only from the output, but also from the weights. And the teacher has the same weights as the student has the same weights as the teacher, then we expect to see they are actually doing the same thing. So here's some notation that I'm going to use for the rest of the presentation. So you have the layer L-1 and layer L. Each of them has n nodes, n L+-1 and n L nodes respectively. Right. So and the weights between these two layers is called WL. Right. So and also for each of these neurons, you can basically put their activations together into one vector, and also put their upcoming gradient as another vector. So that's basically this notation. And the weight updated rule is as simple as the outer product between the input activation F and also the downward gradient G. So if you take the output and take expectation with respect to the input X, you get the gradient of the weight. And for SGD and GD, the only difference here is the gradient is taken over the entire data set or taken over the batch. Okay. So the first thing that we actually find here is that in this ReLU setting, there's actually a very simple, very interesting lemma that we can actually prove. Basically, that lemma actually link the student gradient with the teacher's activation and student activation. So this is actually a very important lemma, and the people actually we actually use that for the second paper, and we are going to talk about that next. Okay. So basically, like the idea here is the student gradient is basically can be represented as a linear combination of the teacher's activation plus the linear combination of the student activation. Because of that, and you can actually use that to prove a lot of interesting theorems. So then I'm going to talk a little bit about what are the conclusions we can draw from this setting. So the first demonstrative case is if you just have two layer network, and the gradient is 0 and also infinite samples. In that case, what are the simplest thing we can do? Right, so here's a demonstrative case. So before we actually can prove anything, I mean, my habit is always to do some empirical experiments. Right, so here's like a very simple 2D experiment to show the alignment is actually happening. Right, so here there's two very strong and thick lines. They are basically the teacher's boundary. Right, they are fixed, and all these dashed lines are student boundaries, and they can move around during training. So you can see that when the training starts, and we see that all the student boundaries start to be aligning with the teacher's boundaries. So until that, when things converge, then you see very clear alignment patterns between teacher and student. And we see there's two different kind of students nodes. So one is the student node that is really aligned with the teacher. That's like the orange one or the brown ones. And also there's other student nodes that are not aligned with any teacher weights. So, but interestingly, this basically these two unaligned or called unspecialized student node, their fan out weights are actually very small or even 0. So, and this is something that we can prove in this two-layer setting. Okay. So here's like another way to show this behavior, right? So if you draw a figure so that the x-axis is a normalized correlation of a student node to its best correlated teacher, and the y-axis is the fan-out weights of the student node, then we see this kind of L shape. So what do I mean by L shape is either a student node is very much aligned with the teacher. In that case, we see like a super strong vertical lines, which show that there's non-zero fan-out weights, right? But on the other hand, if the student is not aligned with any teacher, then the norm of their fan-out weights is small or even 0. That's actually a very interesting phenomenon, and we can actually show that it's actually happening in many, even if the student is larger than the teacher. Right? So people may wonder, okay, how we can prove this is true? So the assumption is the data set is actually pretty relaxed. So we don't really put any parameterized assumptions like Gaussian input, which is actually very restrictive. So instead we say it can be any arbitrary infinite data set. Right? So, but the only assumption here is the data set needs to be 4 ranked. So which means that it cannot be a low rank or low dimensional data set. But this is actually a restricting assumptions which will be resolved in the third part of the talk. So we have another ongoing paper, and the paper is just submitted to ASDAS. So, and another assumption is also not that strong. So the assumption basically say that first we want to have a distinct teacher node. So all the teacher nodes need to be pointing to different directions. So, but that's actually a trivial solution, trivial assumption, because if the two teacher nodes are perfectly aligned with each other, then you can just replace that with just one teacher node. Right. So the second assumption we want to make is the teacher's ReLU boundaries are visible in this data set. So what does that mean? Is that data set actually need to, in this data set, we need to see this nodes are ReLU. Otherwise, you can think that node is actually a linear node, but you don't know that because there's no data that can represent this boundary. So these two are actually very reasonable assumptions. Right? So, and besides, we also have a technical definition called observation, which means that we want to have a student to actually perceive the teacher's boundary during the training. So this is a technical assumption we want to make. So once we have all this, then you can show that the conclusion is if the gradient of every data in this region is 0, right? So basically means that all input gradient at layer 1 is 0 at every training samples, and the teacher node J is observed by student node K, then you can prove the teacher J is aligned with at least another student node K prime. So note that this K and K prime can be different. It's often very different. But as long as the teacher node J is observed by some student, which is actually very possible, even if the student is over-parameterized or over-realized, then the teacher J can be shown to be aligned with at least one student K. So this theorem actually gives you a picture of how things work after training ends. Right, so the training the theorem basically tell you if you have a student that has a wider than the teacher, and you train, and they have the same depths, and they train with L2 norm and to convergence, then what will happen is the teacher, for each teacher node, you're going to see at least one student node to align with it. There could be multiple teacher nodes, that multiple student node to align with one teacher. So that's why it's called the alignment. It can be one to many. But on the other hand, there exists some unspecialized student, right? So which are as shown in the black dots. Right? So all these dots, you can actually have a theorem. The corollary basically say that dots under some conditions will have a zero like fan-out weights. So that's the reason why we see this unspecialized neurons in the original 2D examples. And also, that's also the mechanism from this theory to tell you that why we can do mental pruning in the after the training, right? Because this fan-out weights will be 0, and you can prune them away without changing the output of the data. Okay, so people might wonder, okay, what happened to multi-layer? So actually, the same kind of logic can actually be applied to multi-layer. This is because this lemma 1 is actually very general. It can be applied to arbitrary value deep network, right? So as long as teacher and student, they are of the same depth. So you can actually apply the same kind of logic and to show that the lowest layer also has this property. The only difference here is now this alpha and beta, which is the coefficients, just in front of this f function, they have become piecewise constant. So you need to apply the same logic per region. And you can actually show in the experiment that you can see this kind of L-shaped curve for all the layers from layer 1 all the way to layer 4. So that's actually a very interesting phenomenon that we see. Okay, so people might wonder, okay, what can be useful for this kind of solution? And you can actually use this kind of picture to explain a lot of interesting phenomena. So one of the phenomena people actually wonder is why the solution obtained by different approaches for deep neural network can be connected by a curve, but it cannot be connected by a single line. So this is like a very puzzling kind of behavior that people don't know how to explain. So if you connect the 2 points, these 2 points all have very low loss and can be regarded as a solution. You can connect all these 2 by like one or two different line segments. But if you directly connect the 2 with a single line segments, then you will actually experience like a very high loss here, and then go back to low loss. But you connected like these 2 with kind of curvy trajectory, then you can make sure you can achieve at every point of this trajectory, everything is 0 in terms of loss. So this is a very interesting phenomenon, and people don't really know how can we explain that. However, and with this student setting, it's actually very easy to explain. So this is like one of the ways to explain that. So I mean, because every time you train the model comes to a solution. That solution may have a permutation in terms of specialized, and unspecialized neurons, right? So this kind of shuffling actually creates exponential many local minimas, and each of them are actually very useful, and each of them actually a good solution by its own. But if you want to connect these 2, then you have to go through these 3 steps in order to find a curve that is always have low loss, but at the same time can connect all these 2 solutions together. So this actually is a construction procedure that you can make sure that this curve is doing the things that you want. Right? The idea is very simple. So suppose like you have 3 neurons. Right? In these 3 neurons, the order of unspecialized W and W star, they are different. Then you cannot directly go from solution 1 to solution 2, because if you do that, then you end up with a neural network, so that all of these 3 weights are not specialized or are not aligned to any teachers, and the loss is non-zero. And you see, actually, that's the reason why you see this kind of bump here. But if you do this line segment so that you first convert this unspecialized weights to W1 star, this is possible because its fan-out weight is 0. So if you convert that to W1 star, nothing will change because the output is not affected by this weights. And then once this becomes W1 star, then you can basically move this mass from V1 to V3. V is basically the fan-out weights. Right, so moving these 2 mass is fine because these 2 weights has the same direction orientation. So if you move some of this weights from one to the other, and this won't change the output of the neural network as well. And once you achieve that, then you can go to the final step, in which you can basically change this W1 star to any kind of unspecialized direction. Right. So because the output fan-out weights is 0, so whatever things you have changed in the weights, it won't be reflected to the output of the student network. So this is also a 0 loss curve. So if you do all these 3 steps, then you actually find a curve that connect the 2 solutions. And that's kind of an interesting construction. And naturally is a conclusion from the teacher-student specialization. So, and also we discussed about a more realistic case in which it's still 2 layers, but instead of having 0 gradient, we have a small gradient and also finite samples. So this basically becomes much more realistic. And in this case, I'm going to omit all the details because the proof is kind of complicated, but I go directly to the complexity of 2-layer networks. It shows, it turned out that you can actually achieve polynomial complexity for 2-layer networks. So, so basically the conclusion is like that. So if you have a small gradient, okay, you already trained the gradient so that it becomes super small and smaller than something about epsilon, right? So some kind of constant times epsilon. Then some complexity of this data set needed to achieve epsilon alignment, right, is that it's basically proportional to the polynomial of the number of neurons in a teacher plus student, and also quadratic to dimension, and also inverse proportional to epsilon, etc. But this actually needs some kind of additional condition, which is called augmentation. So you need to do some augmentation around each of the data sets, so then you train them all on augmentation in order to achieve that. Yeah. So, and I'm going to only talk about the intuition. So here, like the lesson, what are the lessons we can learn from the this gradient condition? One lesson that we can learn is that you actually have this alpha here as a denominator. So the alpha is actually the inner product of this fan-out, 2 fan-out weights in the 2-layer setting. Right. So this basically means that strong teacher actually learn faster. So if you have a strong teacher, so which basically means that the magnitude of these weights is larger, right? So if this is larger, then this thing will become larger as well. So if this thing becomes larger, then you actually will see like it's the gradient. Basically the gradient, this condition become a little bit loose. What's it? Because this condition becomes loose, which means that if the gradient goes down all the way to 0, and the gradient goes all the way to here, and the strong teacher already start to specialize with this same amount of epsilon alignment criteria. But for other student nodes that are weak, then this alpha becomes super small. Then in that case, like for the same curve, right? So the weaker student nodes at here, I mean that we have to wait until the training becomes super accurate. Then the weaker student node will start to specialize. So here is like the interesting the demonstration of how these things work, right? So here is basically in this case you can construct a teacher so that the teacher's fan-out weights satisfy this power law. Right, so the weights, the magnitude of this fan-out weights is inverse proportional to 1/j to the power of p, and p is some kind of tunable parameters. Right, j is the index of the teacher. So which basically means that the first teacher node are going to have the highest fan-out weights in terms of magnitude, and the lower teacher node in index will have a lower fan-out weights. So what you see is if the p is 0.5, which means that everything is equal, right? So because the larger the p is, the more polarity between the strong teacher node and a weaker teacher node. So if t is larger, if t is small, then everything converges to their teacher very quickly. They go to 1.0 normalized correlation very, very quickly. But if you tune this p to larger and larger numbers, which means that there's a strong polarity between weaker and stronger teacher, then the student training becomes very interesting. So there's some like a pretty strong alignment for each of the teachers. They are very easy to learn, but there are some teachers are super hard to learn, takes forever until it gets to the destination. This is actually the conclusion you can actually see from the proof. Right? So another lesson that we can learn is from the proof, you can actually show that data augmentation actually matters. Because you can actually do two different augmentations. One is called the teacher-agnostic augmentation, and the other called teacher-aware augmentation. So in these two cases, the augmentation is done in different directions. So this one basically say that the direction of the augmentation is independent of the teacher's directions. But this is basically say the augmentation has to be aligning with teacher's weights. So then the bound is actually become better. Right, so with the wire teacher, so you see like the bound becomes stricter, and also the semi-progressive becomes linear. Right, so this is like empirical solutions about why this is showing that this is indeed the case. So if you use the teacher-aware data set to train the model, you see like the evaluation loss of this teacher-aware is very, very low actually, while the evaluation loss of teacher-agnostic augmentation is super high. It started from like super high loss and then gradually goes down. Okay, this is the normal curve you will see if you have more and more samples. But if the samples are arranged in a very specific manner, then this loss is actually very low in the evaluation set, which is kind of.
Yuandong, can I ask a question here about the augmentation? So how do you define this augmentation in a way to enforce this alignment, right, with this teacher model in the weight space?
Yeah, so basically like the teacher-aware augmentation is kind of like cheating version of the augmentation. So here, like direction of this augmentation aligning with the teacher's weights, right? So supposedly before you train the model, you already know the teacher's weights. Then you use that teacher's weights to align to basically augment the data.
I see. Oh, so this is different from the standard augmentation.
Yes,
where you
exactly.
Got it. Thank you.
Yes. Okay. Yeah, that's the reason why you can get a lower bound. And this one basically saying that, okay, I'm augmenting data, but with the all axis aligned directions. And this direction will be independent of the teacher's weights. So that's the reason why we have higher worse bound. Okay. Yeah. And you can use the same like analysis to show that the small gradient, the condition and complexity is that. And because Q is actually the number of boundaries of hyperplanes in high dimensional, in like a multi-layer setting, and this is actually exponential. So you have to use exponential complexity to solve this. And we also try the same idea try the same experiment on Self-supervised, which see like the alignment actually getting better if you have a wider and wider student network. So basically, partly justify this is the case. Okay, that's the first part of the talk. So in the following, I'm going to talk about very recent work about like using this teacher-student setting to understand self-supervised learning. And this is actually a very interesting work, and we're going to talk a little bit about that. So this work is basically saying that, okay, let's switch gear a little bit. Like forget about teacher-student setting, but let's focus more on the student self-supervised learning. So what we see is that self-supervised learning is actually having a very similar structure right? Then the teacher-student setting, right? So here's like how the self-supervised learning is working. So in this kind of framework, what happens is you have a data set, and you use data set to draw an image. And that image was undergoing two different data augmentations, right? So data augmentation is basically saying, okay, given this X, which is the input, you sample 2 points, X1, X2, and these 2 points are basically being sent to the same network. Sometimes like one network may have one extra predictor. And once you have this same, once these 2 images are being sent to 2 networks, they will give you 2 different outputs. And then you compute some loss for these outputs so that, and this loss can help you in terms of learning a better representation of the data. So this kind of framework is very attractive because no human label is needed. You only need a data augmentation. Once you have data augmentation, then you get data augmentation automatically tell you which 2 images are similar to each other, which 2 images are not similar to each other. And then you can use that to train a good representation without label a lot of things. That's actually very interesting. And the people have already tried this idea for a long time. And very recently, we see 2 different papers. One is called the Similarity, and that is from Hinton's group. And the other is called BYOL, which is a very recent work from DeepMind. And these both papers actually show super good performance when you're actually using this kind of framework to train a representation. So why this is very interesting? People actually have like a lot of questions here, right? So basically, first of all, this seems to be magic, right? So why a good representation can be learned in this way, right? And another question is like, what's the role played by a neural network, by data augmentation, also by training procedure? So you have all these 3 things can piece together, flying around, and you have no idea what's going on. Right? So people actually report a lot of empirical results saying, okay, if you change the training by a little bit, change the data network by a little bit, or increase the augmentation, then things will become better. But we don't know why. And finally, there's like one of the very recent mystery. DeepMind people actually threw that to us is because BYOL in the particular setting, there's even no negative pairs. Right? So in the Similarity setting, what happens is that we want to maximize the distance between 2 images that is augmented from a different input. And you want to minimize the distance between representation of 2 images that is generating from the same input. Right? So this actually provides you with this kind of constructiveness, saying like these 2 should be similar, that 2 should not be similar. But the BYOL doesn't seem to be that. I mean, BYOL actually doing using only like positive pairs, but not negative pairs, which is actually mystery, and still it works. So we already see that there's a similarity between this with the teacher-student setting, right? And if we record a teacher-student setting, we see that in the teacher-student setting, you have a student and a teacher, and the teacher is fixed, and the student is not fixed, and you learn under the SGD, right? So, but now we actually still have this very similar, same 2-tower kind of framework, right? So you have online and also target. But the only difference here is you have both of the online and target networks are training. Right? It's not like one is fixed and the other is training. And also we have augmentation. But interestingly, if you put all these things together, you actually come with a much nicer framework. You actually see a very interesting behavior of how this self-supervised learning actually works. So the first thing that we analyze is the Similarity case. So in that case, it's a very standard version of doing contrastive learning. Right? So the data was basically sampled from this probability distribution P, and the data was basically being augmented into 2 several pairs. Right? So they are all from the same data. But at the same time, you can also sample a different sample from the same distribution, and then you do augmentation. And then the goal here is to basically minimizing the distance between positive pairs and basically the representation of the positive pairs, and then maximize this distance between the representation of negative pairs. So F is basically the representation that is on the last layer of the network. Right. So here we basically omit a lot of details. For example, we want to get rid of like a final few layers in order to get a representation, but we just use simplest case to analyze. And then basically the how we actually do this contrastive learning is basically by this info-NC. That allows actually doing this maximization and minimization at the same time. So the interesting first finding that we actually find is if you just do SimClear And then we can actually compute an analytical form of the weight update at each layer here. That's very interesting because for each of these weights W, and that you can actually write down like what is the exact change of these weights at every iteration. And this exact weight change at each iteration, it can be represented by a matrix product between operator called the covariance operator and the vectorized form of the weights. Right. So that's actually a very interesting thing. And this one is like a covariance operator, which basically is can be computed analytically by following the formulas that we put in the paper. Okay. So then how it is working? So you see, this is the curve. Here's basically like a small picture showing this is how it works. So you start from like a initialization of weights. And then this initialization of weights will create this covariance operator because this operator is actually conditioned on the weights. So once you have this covariance operator, which is always a PSD matrix, and you basically use that to update this WL, and then WL becomes WLT plus 1. And this one will basically update this one, and this will compute this additional covariance operator and repeat. So, and this happens at each layer. So in the deep neural network. So basically, by doing that, we actually open the black box. We actually understand of what's going on inside each layer of the network. That's kind of interesting. And the immediate conclusion we can draw is that the PSD matrix will have all eigenvalues positive, right? So then the natural conclusion will say, okay, the strongest eigenmodes will drive the weights growth along the most promising directions. But then the question is, because here it's all mathematical, there's no intuition. The next question is, what are the strong eigenmodes in the covariance operator we can see given like data generation? Right. So to understand that, we basically need a generative model of the data. So the second part of the paper is about to use generative model to understand the covariance operator. Then we want to construct like what is going on inside this entire self-supervised learning training process. So here, the idea here is first we have a nature. The nature actually generates the data set for you. So you don't know how to generate. But we assume that there's two different variables. One is called Z0, which is a class or sample variable that won't change after augmentation. And the second variable is called Z prime. And that Z prime is actually changeable variables over data augmentation. Right. So for example, if the data augmentation is image rotation, then Z prime can be like the angle of an object in the image, right? So this Z prime will be changed after the augmentation. For example, if you change the image, the rotation angles, then the overall angle of each of the objects will also change. So Z prime will become Z prime 1 or Z prime 2. And this will be sent to two different neural networks of the same architecture. And then the same player will work there. But the Z0 won't be changed over augmentation. So Z0 is here, and then after augmentation, Z0 will remain the same. So this is because, for example, Z0 is from our object labels, right? Then after you do data augmentation, then this object label won't change. You still see, if it's a dog, after rotation, you still see there's a dog. You have this 2 Z0 here. So once you have all these settings, then you can actually hypothesize like a different specific form of the generative model of Z0 and Z prime. And you can basically compute this covariance matrix analytically. Right? So here's like one simple case that you can think about. So this is basically a vision case. So you have two objects in one-dimensional image. And these two objects are actually moving around, translating in this one-dimensional image. So here, if Z0 equals to 1, which means that you are actually perceiving a first object, it has two ones. And these two ones will move around. So you see this this kind of like patterns, right? So this to move around and you go back to this place. And if Z0 equals 2, then you have two other the second object, which is 0, 1, 0. So this is another object. That object also undergoes this translation. So under this kind of analytical, very simple form, you can actually compute this V, the covariance operator, analytically. And this is the analytical solution you can get. Right. So the instant conclusion is you can actually show if you use linear neurons and if you do sim-clear type of training, then nothing is learned because that covariance operator will be 0 precisely. So nothing will happen. But if you have a ReLU network, if you use a ReLU neurons, then it will try to enforce what is initialized. And it will basically enforce them. So if a neuron happen to exclude some of this some of this like data, then it will continue to exclude that. And this entire training will enforce this random fluctuation of the initialization keep up in this entire procedure and become a real feature that we want to use. That's a very interesting behavior that you can see from this analytical form. Okay, so here's like and we also proceed with a two-layer example. So you can actually have, we can actually compute the covariance operator for 2 layers between the top layer and the bottom layer. Right. So remember that this covariance operator is actually defined per layer. So you can actually compute the one for each of the layers, and you can study how they interact with each other during training. So here's like one theorem that you can show if some condition holds, then these 2 operators actually enforcing each other in terms of the training. So I won't get into detail, but the major idea is basically you start with the training, and these weights will be a little bit stronger, right? We're doing a training, and this will actually enforce that these weights become stronger. And this weights become stronger, then this covariance operator in the lower layer will become larger, and this will also accelerate training. So this is actually an interesting behavior that we didn't really see in the 1-layer network, but you actually can see it in 2-layer. And finally, we actually extend this model to hierarchical latent tree models. And in this case, it's, the generative procedure is actually governed by a hierarchical latent model. And this hierarchical latent model can be very deep. Right. So in that case, we can actually do analysis, see like what is going on for the covariance operator and how this covariance operator can learn the important latent variable from the latent model. So it turned out that it's possible that we can show for each of these neurons in the deep ReLU network, some neurons will become an instantiation of the corresponding latent variable. So, but for the time, for limited time, we're going to skip that. I think there's a lot of details in the paper. And finally, we actually use the same framework for analyzing the BYOL setting. So in a BYOL setting, the interesting part here is there's even no negative pairs. So, but one necessary condition for this to work is that this online network has to have an extra predictor. There's an extra layer on the online network compared to target network. So in that case, you only need to use L1 loss or normalize L1 loss. You don't need to use negative pairs, and this still will work. This is very surprising. So why this is the case? Why it won't convert to a trivial solution? So a trivial solution will be the representation of all the images are constant. Then the L2 loss will trivially be 0, and everything is not learned. But that's actually not the case. So then, like we actually use the same framework to analyze that. But by adding like one basically normalization conditions, right? So basically, because the reason why this is the case is the previous empirical result already show that if you add a BatchNorm in these layers, then it will work. But if you don't have BatchNorm at all, but you still train with HGD, this entire framework won't work. So the BatchNorm is actually doing a very good job, important critical job to enforce that this is working. So why that's the case? So we basically say, okay, if you have a BatchNorm, then we can actually correct this gradient by its means. So we basically model BatchNorm as a 0 mean normalization in which the gradient, the bipolar gradient, has to be 0 mean after you going through the BatchNorm. With this condition, then the gradient is changed. I mean, obviously the gradient, the weight update will also be changed, right? So here's like the correction terms that we can compute due to this normalization. So what we actually see is that after this correction, we see these 3 terms. The first term is basically telling you that you have to enforce similar representation within the augmentation. So this term will lead to a trivial solution because you can have similar representation for everything. Then this term is 0, right? So nothing will happen. But the rest 2 terms are going to become interesting, right? So, and especially when there's a presence of a predictor in this weights, and then you actually can show that, and that these 2 terms, one is the positive term is larger than the negative terms. And the positive term happen to be an approximate covariance operator. And that's the reason why this thing will work. And negative term, because it's a second order term for restrictive predictor. If the predictor is a very small weight, then this will be very small, and you just go away, and you only have this one. And that one is basically the key term in the same case so that it will make things work. Okay. So we actually do some analysis, some empirical study to verify this is the case. So as we see, if we don't use a predictor in this STR data set, thing doesn't work. So all this top one performance is like garbage, right? But even if you have a predictor, and also you still need a BN, right? So without BN, you see that performance is still bad. EMA plus EMA is a little bit better, but still bad. But if you plus a BN, then it suddenly become like a pretty good over 60%. But if you put that EMA basically means that exponential moving average. So here basically I omit this the analysis there. But with that usually the performance become better. So this actually justifies that we need to use BN, and also we need to use a predictor. That's a critical thing. And we also use try to do analysis on what part of batch normalization component is actually doing the right thing. Because in our analysis, we only use the fact that the batch normalization will zero mean the forward activation, also the gradient. Right. So then we see if we just normalize the zero mean the activation, what will happen? So it turned out that if you just normalize the activation, you already get like a 64.8. So it's reasonably good. Right. So I mean, of course, if you add like a normalization with respect to mean and also standardization, then you get much better performance. So the effect of standardization is still not known. So we are still working on it. And interestingly, if you do a normalization, but you never normalize the backpropagated gradient, then you see like everything is become like a very, very bad. So this mu slash is basically say, okay, I'm doing like a forward normalization in terms of zero mean, but I will never do a gradient zero mean. Then you see like pretty bad performance, which is consistent, in some sense consistent with our analysis. So we also do analysis on reinitializing the predictor. So the reason why I want to do that is in one of the papers that people that in the original BYOL paper, what happens is that they think the predictor needs to be optimal in order to make things work. But we show that it's not necessarily the case, because you can reinitialize the predictor once in a while, and still you get reasonably good performance. So this is some of the numbers that we actually get. Okay, that's the second part of the talk. That try to use the teacher-student setting to analyze what's going on for the self-supervised learning kind of thing. I think it is a very exciting work, and we're going to keep working on that until we actually understand things better. Now we actually can see what is going on within each layer of the training. That is breaking, opening the black box. And finally, I think I still have maybe 15 minutes. I'm going to talk a little bit about understanding adversarial samples in teacher-student setting. That's a very recent work that we submitted to AI Stats. So adversarial sample is like one of the interesting phenomena of deep neural networks. So what is adversarial sample? Which means that so if you have a sample that is the panda, right? And the interesting part is if you add a little bit noise is super small and not really perceivable to the image, and the image is still perceived by human is still panda, but when you send this image to the network, it suddenly predict a very bad, a very different label, which is called a gibbon. What makes things worse is the confidence of this label is 99.3. It's super confident. So this actually.
Sorry for interrupting here, because I think some folks might have to leave just in case they have questions for you. I just wanted to take a moment to pause here and see if there are any questions from the audience that we can address. Otherwise, we can move on and take advantage of the remaining.
Yeah. No worries. You think let's wait for a while for the folks to ask questions.
And if there's any question from the audience, feel free to unmute and ask. Otherwise, we can move on. I think there's really a lot of interesting stuff packed in this talk. No question? All right, why don't we move on? And maybe let's try to leave 5 minutes for QA session if that's possible.
Oh, yeah, sure. I'm going to cover that part quickly.
Awesome, thanks, Yuandong.
Yeah, so this adversarial sample is kind of a very interesting phenomenon, and this is and also this become a very hard problem for reinforcement learning. For deep learning, especially like if you think about self-driving cars, right? So people have already tried this on self-driving car. They put like stickers on the stop signs. They find that if you put these stickers in a specific way, you can actually turn a stop sign into a 45 mph sign, which is super scary, because then like your system is not working at all. Right? So, and we actually realized that there's actually people who actually use these adversarial pictures to earn money. Right? They print these adversarial pictures to your t-shirts, and then your facial recognition system cannot recognize your face. That's a very interesting application of that. Right? So, and then the question is about like, okay, why adversarial sample exist and how can we deal with that? Right? There's a lot of papers working on that. And one interesting paper that actually give like an interesting hint about why adversarial sample exists is there's a paper called Adversarial Samples, Not Bugs but Features. And so you can take a look at this paper on the internet. And one example it actually gave you is that if you actually compute an adversarial sample, and you can use the adversarial sample plus the wrong label as the training, then you actually end up with a network that actually gives you good accuracy in the correct label data set. So which is crazy, because adversarial labels was regarded as the bad labels, right? And adversarial samples also are regarded as bad samples. If you have two bad things together, you train it, you get like a real good performance in the reasonably in the data set. This sounds like right. So this sounds like a garbage in, a signal out. However, I mean, it's actually very simple to explain if you think with a teacher-student setting. Right? In a teacher-student setting, you assume that data set is represented by a teacher network. Right? So, and when you compute an adversarial input, so for example, for x, you basically perturb that, and then you become x prime, and that x prime, then you use the wrong label associated with this x prime, which is a y prime. And this x and y are bad labels and bad data set, but they are following the correct mapping between teacher student. Right. So, and then you use this pairs to train the model, and obviously this trained data set is still valid, and you can still learn a student network that can do well in the original data set. So for the teacher student setting, it's very natural explanation. So motivated by that, we try to think, okay, how is this connected? Right? So can we use student specialization to actually explain why there's adversarial samples? Right? So basically, like then we try to extend our previous formulation of the student specialization in order to answer this question. So the major improvement here is instead of thinking about the 4-rank input space, right? So we are thinking about this low-rank input space. In the low-rank input space, we are still trying to understand what is going on and with this specialization procedure, right? So, and so what the major conclusion, which is also the first part of the submission, is that we can show theoretically that if the input data are residing in a small subspace, a low-dimensional subspace, then if you check the production of the student node and teacher nodes weights to this subspace, then their difference in terms of the productions are very small. That's consistent with the previous student specialization paper. However, if you project the two vectors to the directions that are perpendicular to the input data subspace, then their angle difference can be very large. This will actually open the door of adversarial samples, right? So because adversarial sample can be the sample that is basically outside the subspace. And this outside subspace, these adversarial samples will trigger different response between teacher and student. And that will lead to very different behaviors of the student network in a data that is outside the subspace. Okay, based on these theorems, I mean, I didn't write the theorem explicitly, but I just want to write this rough idea. So based on these theorems, then we can actually create an empirical model on how the teacher student behaves under this in the low-dimensional input data set setting. So then, like here's like a very empirical model, which says the student network's weight is equals to the teacher network, but plus some kind of noisy terms. And there's two kind of noise. One is like the noise direction is perpendicular to the input subspace, and the other is the noisy direction is that is basically like in this data subspace. So another question becomes, will adversarial training improves the robust accuracy by removing the two? So we actually do a little bit experiment on that. I'm going to omit the details. So I'm going to show you a little bit on maybe this one. So basically this one basically shows that there's a consistency between the robustness accuracy and the alignment, and also the number of epsilon in, epsilon out, which is basically the two parameters in the empirical model. Right. So AT here represents adversarial training, and ST represents standard training. So if you see like in adversarial training, we actually see the epsilon and epsilon out curve are much lower than the standard training, which shows that adversarial indeed like make this alignment much better. And at the same time, you see like the adversarial training's robustness become higher. That's basically like an interesting thing you see, and there's a consistency between the two. Right. So we actually also try like adversarial training with the epsilon in, epsilon out only samples. And it turned out that it's interesting to see that if you use epsilon in only data set, performance is even better than if you're using the standard adversarial training. Then that's actually an interesting observation. So, and also we compare the logic training versus the label training. And we see that logic training really will have a very good alignment between student and teacher, but the label training is not the case. And we are still thinking and investigating what's going on here. So, and here's like a bunch of more experiments. So I think that's it. If you have more questions, please let us know. So we have maybe 5 minutes or 6 minutes to answer the questions.
Awesome. Thanks, Yuandong. This is really a very, very impressive line of work. And I feel like a lot of this work can be expanded into, the talk in its own. And it's really tied well to some of these topics that we're covering this semester in CS839 around data augmentation, learning with less supervision, and also robustness side of the deep learning issues as well, right? So, and actually, for students who are taking the class, and 2 weeks later, we're actually going to dive into some of these topics around self-supervised learning. So I think Yuandong has really kind of provided a nice overview for some of these subjects. And now let's maybe open up the question to the audience. And if you have any kind of remainder question hovering in your mind, I think it's a great opportunity to kind of ask.
Mm-hmm.
I think folks might be still absorbing. I have a question.
Yeah.
I think this the teacher-student training is really appealing, and I've been thinking about this dynamics in this learning process from a student perspective, right? I think one slide that you showed really struck me, this L-shaped curve, right? So to me, it seems like a richer get richer kind of phenomenon.
Yeah, that's right.
My question is, earlier on in this training process, when you start optimize for the student network, what determines why some of the nodes become unspecialized?
Yeah, I think that's a really good question. I think I actually omitted like some of the part of the talk, which is talk about dynamics of the teacher-student training. So that is actually the part that is not published yet, but it was actually in one of versions of the archive. So in that part, basically we analyze like what's going on in this kind of dynamics. So what happens is you actually will see this kind of winner-take-all kind of behavior. So what happens is, after initialization, it will be the case that some of the student neurons happen to be close to the teacher. Some happen to be farther away from it, right? So when the training starts, then these neurons that are close to the teacher, they were going to be even closer. And they said it's kind of like a race. And the network, the neurons that are closer to the teacher, they will race faster and they will reach to the destination faster. So these neurons will become lucky one. And they will say, oh yeah, that's the lucky node, and they actually convert to the teacher, right? So I also see other kind of behaviors, like some student neurons are competing with each other in like specializing into a teacher, but the first student actually works better, and they actually reach the destination, and the second student actually switch the focus to a different teacher. So you're going to see the kind of behavior in a very interesting manner.
Very interesting. And once the neuron become unspecialized, does that like revert ever happen later on in the training process?
It really depends on like how you train the model, right? So SGD, there's a lot of noise there, so it's possible that there could be some unspecialized neuron become specialized again over training. It's definitely possible. Yeah.
Interesting. All right. More questions, folks?
Yes, so I have a question.
Yes.
So in this teacher-student case, so when you're substituting your data with this teacher, so is there a case that you're inducing some sort of inductive bias or some sort of error in the teacher? And if this is the case, how do you make sure it's not transferred to the students and your the students are more robust or learning better?
Yeah, I think that's a great question. I have actually omitted like some of the content in our ASS paper, in which we also analyzed the cases that there could be teacher-student alignment even if the teacher is not perfect, right? So for example, if you have a teacher and you have a student and you actually have some absolute errors which is student training, right? So this actually can model the situation that you have a teacher that is modeling the data, but not modeling the data exactly. But in that case, you can still show will be alignment between teacher and student, but there will be an additional term that prevents you from perfect alignment.
I see.
Yeah. And also another question people might ask is what happens if you have multiple teachers that can explain data? That's actually another question that if you use that framework, you can also show. So it turned out that for every teacher that explains data sufficiently well, you can always use the formula. You can always like use the theorem and show that there will be an alignment between teacher and student. And this alignment will be basically biased towards the teacher that are simple, in which the weights, the fan-out weights are strong, but maybe there are only a few fan-out weights. There's a kind of basically there's one hypothesis of the data, but they were biased towards that. But after you have lost the data and train the model deeper, then train the model longer, then what happens is these student neurons, they were basically finally will converge to the teacher that is not that simple, but actually precisely explain data well.
So just another question on this. So the teacher itself, is there a way to capture the teacher or find a suitable teacher, or is it just like a simple representation for the data?
I mean, what you can do is empirically what you can do is you can actually train over parameterized network on a real data set. Then you can basically get rid of a lot of the neurons, prune these things away, and then you get an approximate teacher. Right. Because you have to basically use the over parameterized network to train the model. Otherwise, this won't work. Right, so over-parameterization is important in terms of like learning a better model. But once you over-parameterize the model, you train it, you have to basically prune all these like irrelevant nodes from the teacher, and so that the rest of them becomes important nodes, and they will become a good teacher to use.
I see. Thanks a lot.
Okay.
All right, I think we're right on time. And let's thank Yuandong again for giving a talk here and spending time with us. Thanks, Yuandong.
Okay, yeah, thanks all for attending, and also thanks Sharon for inviting me.
Yeah, it's a pleasure. And I'll see you guys on Thursday.
See you.
Bye.
Bye.
Thank you.
Oh.